There's quite a bit that can go wrong in this next problem, so let's take our time as we work our way through it and focus on what the key words are. Suppose the maximum weight that a certain type of rectangular beam can support varies inversely. Okay, weight varies inversely is what I'm really looking at first, and I can really ignore that whole second line there as extra verbiage to kind of mess me up. Weight varies inversely as its length, and jointly as its width and the square of its height. Okay, that right there is what I want to focus on. So I've got weight, which I'll use W for, varies, there's my equals K, as its inversely, so that tells me fraction, as its length, and jointly as the width and the square of the height. Now we got a problem here that we got two W's. So the first one is weight, I'll make that a WE, and the second one is width, I'll go W subscript I, just so I don't get these confused with each other. Now I can slide this up here and we can move on to the second sentence. Suppose also that a beam 4 inches wide, that is the width. So let's start substituting things in. We don't know K yet. We're assuming that we're going to have a width of 4 inches. 3 inches high, that tells us the height will be 3, and 18 feet long. Now I'm going to put 18 down in the denominator. Notice that this is in feet and the other ones were in inches, but as long as I stick with that later, things are going to be okay. Can support a maximum weight of 3 tons. Okay, that's what I've got so far, and let's do a little bit of cleanup here. In the numerator I have 9 times 4, 36K, so 3 equals 36K over 18. Therefore, we can simplify on the right, 2K is equal to 3, and K will either equal 3 halves or 1.5. Now let's take that up to the top here and write our general equation. Weight, W subscript E, is equal to 1.5 width, WI, H squared over the length. Now let's read this final sentence. It says, what is the maximum weight? Okay, that's great. The left side is already isolated. That can be supported by a beam that is 7 inches wide. So here's my 1.5, 7 inches, 4 inches high. Notice I'm keeping with the 4 inches high, and 6 feet long. And we said, over on the left this was in feet, so we're sticking with feet over here. So what do we have? When you multiply this all out and divide by 6, the weight is going to equal 28 tons. Let's take our time with this next problem also. The force needed, force, to keep a car from skidding on a curve. Well, we don't really need any of that stuff. Okay, just force varies inversely as the radius of the curve and jointly as the weight of the car and the square of the car's speed. That's a lot, so let's go for this. Force, that'll be capital F, varies, there's my equals K. I see the word inversely, so that tells me I'm dealing with a fraction. Inversely as the radius, that'll be R down in my denominator. And jointly as, that puts me back up in the numerator, the weight of the car, W, and the square of the car's speed. Now usually we use R for rate when we're talking about distance, rate, time problems, but let's use, since R is used already, let's use V for velocity. Velocity squared. And that would be our starting equation. Now let's move to our second sentence. Suppose that 245 pounds of force, that's 245 on the left, is equal to K times, let's see what we've got, 2,000 pound car, that is the weight, 2,000, on a curve of radius 600 feet. I probably should be writing the units in here, but they're going to be the same in the second half of the problem. At 35 miles an hour, there will be my 35 getting squared. Now, let's see what we've got. 245 is equal to, I'm going to do a little bit of simplification here, dividing by 100, which tells me I can cross off some zeros. Multiply 35 times itself times 20 to get 24,500 K divided by 6. And then when I divide through on each side, I can get K is equal to 0.06. Now let's write this as a general equation. Force equals 0.06 WV squared over R. Let's read our final sentence. What force? Okay, force we don't know. We're going to keep the 0.06 there. We'll keep the same car. That tells us the weight is going to be 2,000. 45 miles an hour, so 45 squared at a radius of 900 feet. When you do the division here, you will find that this is going to be 270 pounds of force. Now, after having read this problem through, I noticed we were doing the same car. Had we noticed that at the beginning, we could have just left the 2,000 out of the problem altogether and kept the numbers a little bit smaller. But as they say, hindsight is 20/20 vision.